So hello everyone, welcome to the Spectral Geometry and the Cloud seminar. Today we have the pleasure of having Romain Petrides, who will speak about variational method for functionals depending on eigenvalues. Romain, the floor is yours.
Thank you, Alexandre, for the invitation. I will talk about optimization of eigenvalues. So we have to build some variational methods for that. So I would like to start with, a state of art, a lot of examples in order to give a motivation for all the presentation and all the results I present in the end of the presentation. Some of them are well known for some of you, but I start from the beginning of the story. So let me talk about optimization of one Laplace eigenvalue on surfaces, depending on Riemannian metrics. So I will give some tables in any frame. The first one here is for the for one Laplace eigenvalue. So the functional here is one Laplace eigenvalue, but it is a renormalized eigenvalue. So we take a compact surface, dimension 2, without boundary, and when we have a Riemannian metric, we have eigenvalues, which is a sequence of eigenvalues. Everybody knows that. And when we want to make a variational method on eigenvalues, we would like to fix something. So, for instance, the area. So multiplying by the area is the same thing as taking a metric with a fixed area, for instance. So the functional we consider is lambda k bar, the following renormalized eigenvalue. So on the right side, I put the associated critical points for this functional. So we will see that, but the eigenvalue functional is not a C1 functional. So that the notion of criticality is not the classical one, but I will give information for, a good definition for it. But in 1966, Dirichlet gave a definition for critical metrics, and he proved that if metrics are critical for this functional, then they are induced metrics of minimal immersion into a sphere by kth eigenfunctions, where k is the index associated to the eigenvalue function. So next. Then I have some places for bounds on eigenvalues. So if you try to minimize the eigenvalue, then you always have 0 because of Cheeger dumbbells. But when you maximize, you know that we have an upper bound. So the following authors worked on upper bounds. The first one was Hersch for the sphere for k equal to 1. Then Yang and Yao and Li and Yao worked for k equal to 1, so with different methods. The first one, Yang Yao, generalizes the method on the sphere, and the Li and Yao paper worked on the conformal volume, which is a maximizer, an upper bound for the first eigenvalue. And then in 1993, Koreva proved the upper bound for any k. And Hassanizad gave some improvements of this bound. On the right side, you have optimal bounds. So when you are looking for bounds, you want to improve them. And we have exact bounds for the sphere, for the hyperbolic plane, the torus, the Klein bottle, and surfaces, orientable surfaces of genus 2. So we have two questions for maximization. We look for optimal bounds, and also we look for existence of maximizers if we have optimal bounds. So I proved some results for k equal to 1 in 2014, and then for higher indices. And next, I would also like to talk about restricted context. When you are working on the Laplace eigenvalue with a conformal constraint, you still have interesting critical metrics. So you take the same functional, the lambda k bar, which is written as the last line of the section functional, but we specify this functional to conformal metrics. So this functional only depends on a function on the manifold, a smooth positive function, and you want to maximize it over all the smooth positive functions. And without maximization, if you just consider the critical metrics, you have that the conformal factor is in fact the density of energy of harmonic maps into a sphere by case eigenfunctions. So this result was proved by Dirichlet and Elias. And also for bounds, it's the same result as before. Mainly Correva, who proved all the results for any k. And for optimal bounds, I would like to focus on the sphere and projective plane, which only have one conformal class up to diffeomorphism. And there is the classical result by Hersch, where the maximizer is the round sphere. The result on the hyperbolic plane, where the maximizer is a round metric too, and it is the only maximizer as before. I proved the result for a result of rigidity result on lambda 1. It is far from the one of the sphere if the surface is not conformal to a sphere. This result is important to have compactness results and to prove, for instance, existence of maximizers for the first eigenvalue. Then, if we are interested in higher eigenvalues, there is this result by Karpukhin, Nadirashvili, Penskoy, Polterovich, who proved that lambda k is equal to 8 pi k, and there is no maximizer in this case, and that's the way you prove that the bound is 8 pi k, in fact. But we know that the maximal configuration corresponds to k disjoint round sphere of same area. We have the similar result by Karpukhin for the projective plane, where we have one projective plane and k minus 1 spheres. The result for existence of maximizers, so similar result as before by myself in a conformal class. In fact, the result I obtained for any metric are a consequence of this result in the conformal class, because I maximize first in the conformal class and then among all the conformal class in dimension 2. But okay, and there are also other results, and I would like to mention the result by Karpukhin and Stern, who proved the existence of maximizers for k equal to 1 and 2 by other methods, by a min-max method on harmonic maps, which give more information on maximizers, and it's very interesting. Next. And on Steklov eigenvalue, so you understood that I made a large state of art, but maybe I forgot some people, but I'm sorry for that. But it's just to put the problem here and to see that I want to, to make a very general overview on these problems. So the functional here is the case Steklov the functional here is the case Steklov eigenvalue renormalized by the lengths. In this case, Fraser and Shane noticed that the critical metric are induced metrics of free boundary minimal immersion into ball by case eigenvalue, by case eigenfunctions associated to the eigenvalue functional. For the bound, we have classical bounds for Stekelov eigenvalues, and we have more recent bounds given by Girard, Polterovich, Fraser, and Shane. Also optimal bounds. And recently, optimal bounds for genus zero surfaces with some boundary components, and when the number of boundary components goes to plus infinity, an exact bound by Girard and Lagacé, and also proof of existence of maximizers with the same model as for the Laplace eigenvalue by Fraser and Shane and myself. Next. I also gave a presentation some months ago about a combination of Laplace eigenvalues, and combination of Stekelov eigenvalues is the same, follows the same principle. If you try to minimize, in this case, a combination of eigenvalues, so it is a functional which is like from to a metric G, I associate f of lambda 1 of G, lambda 2 of G, etc., lambda m of G, so it depends on G, where f is a function which is decreasing with respect to all the variables. It is a C1 function. And in this case, so I gave examples of functions that could appear. If you go to the section optimal bounds, so there are other optimal bounds we can prove this case, but there is a classical one by Hersch. If you do combinations of 1 over lambda 1, 1 over lambda 2, and 1 over lambda 3, then the minimum is realized by round spheres. So what I noticed, excuse me, I just go back. Just what I noticed is that critical metrics in this case correspond to minimal surfaces into ellipsoids. And I prove with the same model as before, existence of maximizers. Minimizer in this case. I also mentioned the conformal Laplacian. Because when you are interested in higher eigenvalues, you know that the Dirichlet energy is not conformally invariant, and we can guess that the natural operator to consider to have some geometric things is the conformal Laplacian, because it is conformally invariant. And that's what people did in the past. They normalized by Ziria the case eigenvalue associated to the conformal Laplacian. In this case, they proved that they are associated to harmonic maps into spheres. But in this case, we know that the conformal Laplacian is not always a positive operator. So that we have to distinguish some cases. But in any time when you optimize the first eigenvalue, so the first eigenvalue associated to the conformal Laplacian is equivalent to solving the Yamabe problem. So looking for a metric which has constant scalar curvature. But you don't know if the first eigenvalue is positive or negative. What we know by result by Kanzani, Gover, Jacobson, Ponge is that the number of negative eigenvalue is a conformal invariant. So that the conformal problem is a good problem. Optimizing with respect to all conformal metric conformal to one metric. What we have to distinguish, excuse me, just before, is that if you minimize, if lambda 1 is positive, you have to minimize, and if lambda 1 is negative, you have to maximize. It's a good problem. And what did Arman Humbert is the minimization of positive eigenvalues when you know that the second eigenvalue is positive. And Gursky-Perez worked on negative eigenvalues. when the Yamabe invariant is negative and when we know that the second eigenvalue is negative.
Romain, I have a question. If you have lambda1 bigger than 0 and you try to maximize, what happens?
It goes to plus infinity.
Okay.
Yeah, it's the bound I put there. I do not remember. I think it's Aman-Jams.
Okay, thank you.
And it's the same if you try to minimize negative eigenvalue, it goes to minus infinity. And then in fact, we can do something in higher dimension for the Laplacian, and that's what I give here. So the critical conformal factors are again associated to harmonic maps into a sphere. It's a result by Soufi and Ilias. We have a bound given by Koreva and all others that work after. Optimal bounds are natural for instance, for the conformal class of the round sphere. It's the round metric. You also have the rigidity results. And I gave just recently existence of maximizers. So you have other difficulties to overcome for that. And that's what I would like to talk about. So next, and before I would like to talk about the main difficulties for a variational approach for eigenvalues. So I take the simplest example I know, Laplace eigenvalue on surfaces. So when we take a maximizing sequence, what we can do that, after a normalization, we can assume that the sequence has mass 1 because the area of the surface is 1, and you can renormalize. But in this case, the adapted space of variation is a space of probability measures. The problem is that this space is too big because if you let it converge to some measure, you do not know if at the limit you have a first eigenvalue. You have a first eigenvalue, but if you have eigenfunctions associated to these eigenvalues. And what we know is that in variational methods, we would like to prove that in a bigger space it converges, and then when you have convergence to something which has weak regularity, we expect that the Euler-Lagrange equation associated to the maximizer give you regularity back. But here it's not the case. And other difficulty, the eigenvalue equation satisfies this PD. So you cannot prove something for convergence of e to the 2un more than it converges to a measure, which is not good. Moreover, we can try to work on the eigenvalue function equation because it's an elliptic PD and expect for regularity from this equation. But in this case, there is also a problem because it is a supercritical sequence of PDs in the sense that e to the 2un is only bounded in L1. And even if you know that phi n is bounded in infinity, you do not have it. But if you know that you have it, you cannot have higher regularity because e to the 2un is bounded in L1, so that the Laplacian is bounded in L1, and you do not have anything. But here, what we can expect is that you are close to be a to be a critical metric. And if you just assume that e to the 2un is a sequence of maximizers, then it satisfies the Euler-Lagrange equation. And the Euler-Lagrange equation is exactly phi n squared equal to 1, where phi n is a sequence of a family of first eigenfunctions, of case eigenfunctions. And when you compute Laplacian of phi n squared equal to 0, then you obtain that gradient phi n squared is equal to the conformal factor. So
I have a question.
Harmonic map equation. Yeah.
You said that 2un is a sequence of maximizers or a maximizing sequence?
No, I assume in this case, just to explain that we can expect regularity when you are close to be maximizers. But here, I just assume that you are maximizers.
Okay, thank you.
You just prove compactness of maximizers. And there is compactness in some sense because it satisfies the harmonic map equation, and because we have all the PDE results on harmonic map equations and all these asymptotic results on it. Notice that in this case, the PDE is also critical. So it's difficult even for this PDE to have something, but there is a structure that allows you to make regularity estimates for this equation. So what we would like to do is, to build a maximizing sequence, which is not a random one, but a maximizing sequence which is close to be a critical one. So the previous method always took this way. First, we regularize the functional by some parameter. So for instance, we regularize the natural space of variations, so that, for instance, we restrict the conformal factors to be in L infinity. And you bound it by some big N, and you let then N go to plus infinity. Or you regularize the functional. For instance, you use the hit kernel. So you regularize conformal factor by the hit kernel, and then you maximize it. And then the second point is that when you build this sequence, it satisfies some Euler-Lagrange equation in some sense, because it is a maximizer for the regularized functional. And you use this equation, which is close to be a harmonic map equation, to let it converge as the parameter goes to plus infinity or 0. And I just give an example. So the regularization by the hit kernel. And after some work, we obtain a maximizing sequence which satisfies the following conditions. So we have existence of phi epsilon, such that, such that so it satisfies the eigenvalue equation. And you have that phi epsilon squared is bigger than 1 minus delta epsilon pointwise, where delta epsilon goes to 0 as epsilon goes to 0. So if you have exactly phi epsilon squared equal to 1, then it is a sequence of harmonic maps, so it's okay. But here it's not exactly that, but it's pointwise close to 1, but just on one side. And there is the integral thing that lets you, on one side it's bigger than 1, but there is the integral that forces phi epsilon to converge to 1, in fact. Okay. So I would like to give a new approach, because the previous approach are very technical, at least for the kernel method. But I also would like to simplify, unify all the previous methods in order to generalize them to other operators, higher dimensions, min-max variational problems, etc. So before explaining what happens for eigenvalue, I would like to recall classical variational methods. So for instance, I work on the nice book by Struve, variational methods. Mostly the results start with let E be a C1 functional on a Banach space. And we say that X is critical if the E of X is equal to 0. So you see the problem here with eigenvalues. We know that eigenvalue functionals are not C1 functions because of crossing of branches of eigenvalues. So I will come back on it just after. So in the classical methods, if you assume that, then you have a deformation lemma. So you take a value, C. So it is a value of the functional, some sense. And by the deformation lemma, so you assume that there are some constants such that E is very close to C. And the derivative of E at that point X is large in some sense. It's far from being equal to 0. So you are far from being critical. Then the deformation lemma tells you that you have a diffeomorphism. so a kind of flow that make that make all the space close to C go below C, but far below C. If you look at it, so the first point is that where you are far from C, then the flow is a constant flow, nothing changes. When the flow always reduces E, and also when you are close to C, you go below C, but far below C. And to prove that, you just use a downhill direction for any point, and then you regularize all the downhill directions to have a vector field, and eta is just the flow associated to this vector field. So next, so the application of this lemma is for variational problems. Like you put C as a critical value. It's an infimum. It's not a critical value now, but you would like to prove that it is a critical value. Take C, the infimum of the supremum of something, of the functional. And the application of the deformation lemma is that if you have good assumptions on the space of variation, then you have a sequence, so which is close to C, such that the differential at x epsilon is going to 0 as epsilon goes to plus infinity. So you are close to be critical. So we say that such a sequence is a Palais-Smale sequence. So it's very classical, but I recall that. Examples, if you take A, the space of singleton, then in fact you do minimization. But you have a minimizing sequence which satisfies something else, like dE goes to 0. So that's what we would like to have for eigenvalues, because we would like to have something which is almost harmonic for Laplace eigenvalues. If you choose something else,
can you show the previous slide again for a second?
Yeah. So it's the application is just the contrapositive of this deformation lemma.
No, it's just
that
how is eta continuous if it fixes the points which are above level C plus epsilon, and then there is epsilon and epsilon 0.
Yeah, and the homeomorphism eta depends on epsilon.
Okay, I just had trouble reconciling the first dot with the last dot. Like it moves things by a lot. For all epsilon, there is. Oh, for all epsilon, you can construct eta.
Yeah,
sorry,
eta depends on epsilon. It's not yeah. I did not put eta index epsilon, but it depends on epsilon, of course.
So Romain, this is like in Morse theory when you attach handles and you deform near critical points, right? In a finite dimensional.
It's a homotopy around non-critical points.
Yeah.
Yeah, it's
homotopy sublevels.
Yes.
Yeah, thank you.
It's what you expect in high dimension. Yeah, in infinite dimension. And if you put ax not x1 this, it's the mountain pass lemma, which is classical for analysts. So the problem is that for eigenvalue functionals, you do not have C1 functionals. So the idea was to use generalized gradients. So they are defined. Clark defined it in the 80s. So I would like to make a drawing just here to say that eigenvalue cannot be C1 eigenvalue, because if you make a variation in one direction, you know that there are branches of eigenvalues that can intersect, and the places where there is multiplicity, there is no smooth functional. So it is local ellipses. And for local ellipses functional, Clark defined the generalized directional derivative, which is a kind of Gato derivative, but not exactly. It's a general Gato derivative, and a subdifferential, which is inspired by a subdifferential in convex analysis. So it satisfies good properties to generalize the gradients for local ellipsis functionals. So next, so I give just examples to make ideas. So very simple examples. If the functional is C1 functional, then the subdifferential is just contains just the differential. And if you take the absolute value, so the drawing of eigenvalues is that it resembles to the absolute value. Then the subdifferential is just the convex hull of the left and right derivative. So definition, we say that X is a critical point for E if 0 is in the subdifferential. So for the absolute value, you see that 0 is in the subdifferential, and you expect 0 to be a critical point because it is a minimizer for the absolute value. So for instance, thanks to this definition, maximizers and minimizers are critical points. And the question I ask, can we compute this in the context of eigenvalue functionals? So give something precise. Can we define an adapted norm of the subdifferential in order to define Palais-Smale sequences? Because in the previous methods, when you take a downhill direction, etc., you have Palais-Smale, you obtain Palais-Smale sequence associated to variational methods, and the norm goes to 0, and you want to make a sense on it. And then once you have it, do we have convergence of Palais-Smale sequences in order to let a sequence of metric converge to a smooth metric? So for the first question, computation of subdifferential, we have a work in progress with David Theodrose. First we give refinements for computations of the subdifferential, because when you have eigenvalue functionals, it's specific. We will have more properties than for local ellipsis functionals. Then we notice new geometric interpretations for combination of eigenvalues, etc. And we try to do a unification of all the previous results in computation of critical metrics in order to have a strong framework to work on in this context. So I give an example to give an image of what happens. So when you take E, the kth eigenvalue of the kth renormalized Laplace eigenvalue, then the subdifferential is included in the convex hull of this. So lambda k bar times 1 minus phi squared, where phi is a normalized eigenfunction associated to the kth eigenvalue. And we also know that there is equality if lambda k is strictly bigger than lambda k minus 1. And in this case, if you look at critical metrics, it's 0 belonging to the convex hull. And this means that there are eigenfunctions such that, there is a big phi such that the coordinate are eigenfunction and phi squared is equal to 1. So you have a map into a sphere, and by the previous computation, you prove that this is a harmonic map. Okay, so for the second question, generalization of Palais-Smale sequences. So there is one difficulty because we consider a space of positive functions. So we do not want to have variations such that the function becomes negative, because you work on conformal factors, and the eigenvalue is only defined for conformal factors. So when you take a direction, you would like e to the 2u plus tv to be a positive function for any t, any positive t. That's why at the neighborhood of e to the 2u, I restrict the space of variations. I take positive functions such that I mean they are normalized. And then I am inspired by I mean, the definition of the norm of dE of x, and I define this as the norm. And it is a good, I mean, it's adapted for the variational method. So we obtain a Palais-Smale sequence, for instance, for optimizations, minimization and minimization. And the question is the third question: do we have convergence of Palais-Smale sequences? So I assume that e to the 2u epsilon is a Palais-Smale sequence in the problem of the Laplace eigenvalues on surfaces, and we obtain exactly that. What I mean, the property I gave you for sequences coming from regularized functionals. So they are Palais-Smale sequences. But we can prove results to all Palais-Smale sequences, convergence results for all Palais-Smale sequences. So the goal on this sequence is to prove that, okay, lambda epsilon goes to lambda. If you have bound and eigenvalues, you have it. Phi epsilon goes to phi. You would like to use the elliptic PDE, so Laplace phi epsilon equal to something in order to get a regularization and let phi epsilon go to phi in some sense. You know that e to the 2u epsilon converges in weak star sense of measures. And then you would like to pass to the limit on the equation and have Laplace phi equal to nu lambda phi and phi squared equal to 1. And then again, computing this, you obtain that nu is equal to gradient phi squared over lambda, so that you have a weak harmonic map equation, which gives you a strong harmonic map equation, and nu becomes a smooth function, and you end the problem. So it is the goal. Now, yeah. In fact, now I wanted to, I mean, to write the proof with the tablet. So it's difficult now.
You can, so you
Yeah.
can use the annotate function of the Zoom if it's possible.
If it's possible, I try to do it. Yes. But do I have the authorization to do that? Yes. I do not know exactly where I go for that. Ah, yes, I have it. Okay. So let's this where omega epsilon is equal to the norm of phi epsilon. In fact, this is very useful to have that pointwise phi epsilon is bigger than 1 minus delta epsilon, because it is not equal to 0, so that you can divide by this norm. And the goal is to prove that this converges to 1. And with a very simple trick, we can prove that in fact phi epsilon is close in H1 to phi epsilon over omega epsilon. And we can also prove that omega epsilon is small in H1. To prove that, we use, the equation and this. Then once you have it, so you replace phi epsilon by phi epsilon over omega epsilon, and it becomes a, L infinity function. So it is closer to be harmonic in some sense. And then, so let me write here. Is it okay for you? Okay. Then the idea is to work locally. So let me work close to some point P, and I would like to compare phi epsilon over omega epsilon to the harmonic replacement of phi epsilon over omega epsilon. So I define the harmonic replacement as a map here, such that it is equal to phi epsilon over omega epsilon on the boundary. And I assume that psi epsilon is harmonic. And the goal is to compare phi epsilon over omega epsilon to psi epsilon. If I succeed to prove that this goes to 0, then I use all the regularity properties on psi epsilon, and then that proves that phi epsilon over omega epsilon converges. And the trick to do that is to use the energy convexity, which is a kind of generalization of what happens for geodesic. You know that if on a manifold you are less than the injectivity radius, then when you take 2 points, there is a unique minimizing geodesic between them. It's the same from harmonic map in some sense. If you assume that the energy of the harmonic map is small, less than some epsilon naught, then you know that there is a unique minimizer, and you have a kind of convexity inequality. Something like this is controlled by the integral of this minus the integral of this. Oh, there is a 2 here. And if you succeed to prove that this goes to 0, it's okay. But using this equation, we can prove that this goes to 0, in fact. So I do not go further in the proof, but main idea is kind of replacement and compare to harmonic maps that converge inside that converge locally. And then when you have, when you have that the energy is small, when you need that the energy is small, you need that there is no concentration. And that's why there are we have to deal with concentration phenomena and bubbling that could appear. And that's why sometimes you do not have any maximizers, you have bubbling. And you have, maximizers which are non-connected surfaces. Okay, so you can go to the next slide. Yeah, okay. Just some few words for higher dimension. So we have the problem in higher dimension where the conformal factor is both in the numerator and the denominator in this case, because the Dirichlet energy is not conformally invariant. And you are normalized by the volume, which is the integral of e to the nu to the 2 over n. So next. So main difficulties. The conformal factors appear in the eigenfunction in the PD associated to the eigenfunction. And it appears in the dimension 2, it appeared, but in dimension n, it also appears in the divergence term. And that's what I wanted to say and to emphasize on, because you may have degenerations inside the divergence term, so that the elliptic PDE is in fact not an elliptic PDE, it's almost elliptic, in the sense that the conformal factor could go to 0 or infinity, and it's a nightmare. And also another problem is that in dimension 2, we had bounds in multiplicity of eigenvalues. That's why the maximizing sequence, the eigenfunction that appear in the Palais-Smale sequence are a finite number of eigenfunctions. But in this case, a priori, you don't know it. So it's also a nightmare. And there is another problem, which is technical. When you do a variation with respect to the conformal factor, you do not obtain good critical metric. So that's the trick by Karpukhin and Metra that give you a way to solve this problem. You have to split the conformal factor into two functions, alpha and beta. And when you look for critical matrix for this functional, then you obtain that we obtain n harmonic map in this case. And if you just put all the theory I gave you before with Palais-Smale sequences, etc., then you can do something and prove existence of maximizers for Laplace eigenvalues in a conformal class. Because in fact, if you have a maximizer for, this functional with alpha beta, it is in fact a maximizer for the previous functional. It's a miracle that appears in this case. Thank you for your attention, and I would be happy to answer your questions.
Thank you very much, Romain, for the talk. So we thank the speaker. Does anyone have questions?
Can I ask one?
Yeah.
So I'm mainly interested in the issue of multiplicity of eigenvalues. Is your Palais-Smale technique essential to circumvent that?
No.
No.
It's essential in the sense that the previous methods were not okay to deal with that, because I told you that if, for instance, for the hit kernel trick, you have a maximizing sequence that satisfies some Euler-Lagrange equation, and I proved that with some work we proved that it is a Palais-Smale sequence, but this work does not work in higher dimension in some sense. That's why I have to take Palais-Smale sequences, and it helps to have the result, but it's not linked to multiplicity. For the multiplicity, I just proved that I don't care. In fact, I let all the eigenfunctions that appear, I have a harmonic map into an infinite dimensional thing, and a posteriori I proved that in fact it was finite dimensional and it's okay.
Okay, so the key difference is that you need to know that the sequence is Palais-Smale in a sense in order to apply the limiting part of the argument in 2 dimensions. Right, the idea to take the limit is still similar to 2-dimensional case.
Yes, once you have that it is a Palais-Smale sequence, okay. Yes, it is similar, but you don't need the hit kernel and all the technical things that appeared in all my previous paper. Okay,
so the main technicality there is that it satisfies the hit kernel implies Palais-Smale. No longer needed. You just start from Palais-Smale and you just do that.
Yeah.
Okay. Thank you.
Romain, I have a naive question. In nonlinear PDEs, sometimes the critical point theory is used to detect new critical points from non-critical points using, I don't know, mountain paths or things like this.
Mm-hmm.
Do you know if here there will be examples where we find new critical situations because we know the structure of the functional, and we can apply some minimax to obtain not minimizer, but saddle points and things like this?
It's a good question. I'm looking for it. In these problems, you know that we can prove existence of maximizers, but we can also prove other things like my theorems were like if we have a strict inequality, then we have existence of maximizer, but we can consider also that if you do not have maximizer, then the inequality is an equality in fact. So we can use this technique not only to prove existence of maximizers, but also to get bounds in some sense. So there is a very large scale of applications. And to answer your question, I did not prove any existence of maximizer, of new critical metrics which are not maximizers. We know, for instance, that the flat torus with respect to all the metrics is a critical metric which is not a maximizer.
Mm-hmm.
But building something new was not. I did not do that. I'm interested in doing that in some example, of course. but I do not have any results just
Because
now.
presumably
But
it could
it's
give
very
you
interesting for maximizers and minimizers, so that's why
yeah, okay.
it's a good first step to apply the method.
Thank
In
you.
fact, we have Palais-Smale sequences, we can make it converge, but what happens is that you can have bubbling. You can, I mean, you can have many things, but I mean, a critical thing, I do not have it exactly. Removing bubbling.
Does someone else have a question for the speaker? Well, in that case, we can thank Romain again.